the expression for the trace of the stress tensor. Okay, before getting there, just let me, one little thing about the spins and dimensions. We got a bit confused last class. Let me say it more clearly. Okay, let's use the symbol delta to denote the weight of an operator, a primary operator under Weyl transformations. So this couple G mu nu and O, this O could be a scalar or it could be something with some arbitrary spin. We'll deal with things. So let's suppose that this O has spin S and S prime, which means it has S lower Z indices. It's a tensor with S lower Z indices and S prime lower Z bar indices. Okay. If this guy has weight delta, then this is the case that we have e to the power 2 phi G mu nu times O S S prime e to the power delta phi. And as always, this arrow means that we get the same correlation functions starting with this couple. Okay, so we put lots of insertions of O on that metric, or lots of insertions of O SS O times e to the power delta phi on that metric. We get the same answers for the correlators. Okay. Now you remember, to make this conformal transformation, we did something else. We imagined we had, let's say that in this metric the coordinates were Z prime, and we did the following. We imagined that suppose e to the power 2 phi was equal to del f by del Z prime del f bar by del Z bar prime. So f and f bar are some functions. They're the functions we'll call Z and Z bar, the new coordinates. Okay, we're specializing to the study of such Weyl transformations that can be written in this form. In that case, we can just take this side and move to the coordinates Z and Z bar. Okay, what's the metric in the so this was always true, but now we'll specialize to delta. So the starting metric was delta. Okay, and then we use the fact that e to the power 2 phi, the metric was dz prime dz bar prime, which is the same as e to the del f by del z dz del f bar by del z bar dz bar, which is the same as dz bar dz dz bar. Right, because f was, this was prime, and f was z, just the chain rule. I could have written df bar if you prefer. Z and f are the same thing, right? I write f just to emphasize the function of z prime. Okay, so this is just a coordinate change. Had O had no indices, this is the case we'd studied before. Okay, then we would have concluded that O of z bar. So now z is f of z prime. Z prime, f of z prime, f bar of z bar prime. Okay, times this e to the power delta times phi. Okay, so that would be del f by del z times del f bar by del z bar. That's e to the power 2 phi. So divided by delta by to the power delta by 2. But this guy and the metric delta was equal to delta with that guy. Okay, so this was the case when O had no indices. Right, this is the case we studied before. But now suppose we work with the case where O has indices. Then this coordinate transformation from here to here is not correct. It needs to be supplemented by additional terms. Okay, so what are the additional terms? Well, let's see. So suppose you imagine that O had S Z indices and S prime or S bar, Z bar indices. So suppose we had that this O prime here, okay, that this O prime here had Z prime, Z prime, Z prime, S of these, and Z bar prime, Z bar prime, S bar of these. Okay? Now, this object, that object there, when we do the coordinate transformation, is not just O of this, but it has the extra tensor transformations. So what are the extra tensor transformations? Well, that's the extra factors of del F by del Z prime to the power S, del F bar by del Z bar prime to the power S bar, times O with all the Z's and Z bars, F of Z prime, F bar of Z prime. Is this clear? Right? This was a del Z that cancels this, makes it a del Z prime, and S times, and S bar times. Is that clear? So, the full relationship will be the following. The full relationship will be delta mu nu O has the same correlation functions as now we've got this term that came just from the Weyl transformation, that's unchanged. But in addition, we've got these pieces. So we have del F by del Z prime to the power delta by 2 plus S, del F bar by del Z bar prime to the power delta by 2 plus S bar times this O with the same argument. Is this clear? Okay. Is the coordinate transformation. You see, a conformal transformation is a compounded Weyl transformation plus coordinate transformation. We previously worked with the case of scalars. Those scalars transform trivially under coordinate transformations in the sense that all that happened is that they move to another position. Okay? However, now when we look at objects which have indices, the indices also transform. Okay, so that adds up there. Okay? So the net conformal dimension, if you take an object that has S lower indices and S bar lower indices and has Weyl transformation delta as defined up there, then it will transform with H is equal to S plus delta by 2 and H bar is equal to S bar plus delta by 2. Okay? The total energy of this operator, H plus H bar, okay? So the total energy operator, the total weight under scale transformations. Okay, so the energy operator, or delta operator, let's call it, is H plus H bar, which is S plus S bar plus delta. So in the case that S and S bar were 0, the scale transformation was the same as the weight under Weyl transformations. When S and S bar is not 0, that's it. There's a small change. Okay? So in particular, as we will see in examples, the stress tensor has a weight 2. It also has spin 2. So this formula is going to be, I'm talking the analytic part of the stress tensor, the ZZ component. Why does it have spin 2? Because that's 2 Z indices downstairs. Why does it have weight 2? Well, we've seen a million times. It has weight 2. For instance, there was 2T in the OP. Okay? And this tells us that the Weyl transformation weight with little delta is 0. Okay? We will see this when we study examples, for instance. The stress tensor will be made up of derivatives of objects, which themselves, we will see this. Okay? So all of its weights coming from its tensorial transformation properties, except for the fact that it's not quite, doesn't quite transform like a tensor. Okay? So that's the part we're now going to try to uncover. But just because I got a bit confused last time about indices, I thought I would clear this up. And a couple of people asked me questions about it. Is this clear? Okay, excellent. Now we are going to discuss how the structure of the OP at non-zero central charge forces the trace of the stress tensor of a conformal field theory to be non-zero, but a very simple non-zero quantity. Okay, just a pure number, a number determined by the geometry of the manifold. Okay, we outlined the main idea last time. I'm just going to go through it again. Yeah, I'm going to go through it again. Remember that we had that T of Z, T of 0 was equal to C by 2 by Z to the 4. Somebody, Vipul pointed out I kept writing C by 12, it's C by 2. Yes, C by 2 by Z to the 4 plus 2T of 0 Z squared plus del T Z. And as we discussed in the last class, these terms capture the transformation of the stress tensor under a translation or a scaling of Z, okay, with weights too. These are perfectly easy to understand terms. They come from the tensorial transformation properties of T with, as we've just explained, with assuming that T does not have any Weyl transformation. Okay, but there's that other irritating term, that C by 2 divided by Z to the 4. This term tells us that if we look at the symmetry with epsilon of Z T of Z, the current being epsilon of Z T of Z, it tells us that the transformation under that symmetry, okay, that the transformation under this symmetry is, let's see, so we want the pole from here. So we want C by 2 epsilon of Z by Z to the 4. And we want the term that's the pole. We get a pole by Taylor expanding to third order. Because this is Z to the 4, we want to cancel 3 of the Z's. So we get triple prime of Z by 6, because Taylor expansion is a 3 factorial. Okay, so we get the transformation of T under this symmetry is equal to epsilon triple prime C by 12. And epsilon triple prime C by 12 multiplying what operator? Multiplying no operator. Multiplying identity. The fact that this multiplies identity makes this very simple. Tells you it's sort of universal. It's got nothing to do with the detailed structure of the theory. Is this clear? So we see that under a combined transformation of the form we just described above, when this f was infinitesimal, 1 plus epsilon, f was infinitesimal, f bar was whatever it was, we're not even to worry about it. Okay, so this f was infinitesimal. When this f was infinitesimal, 1 plus epsilon under such a transformation, there is a change in T. So T is not completely neutral under Weyl transformations, because the first two terms have completely exhausted its tensorial transformation properties. Okay, what remains is the Weyl transformation. So it changes under the Weyl transformation, now we have to track it down. Okay, great. So what was the Weyl transformation associated with this epsilon? Well, remember the Weyl transformation was e to the power 2 phi was equal to del f by del z prime del f bar by del z bar prime. Right, this was the Weyl factor. Okay, we did a Weyl transform, there was a change under that kind of Weyl rescaling. But because we're looking at these infinitesimals epsilon, this is the same as e to the power 2 phi is equal to 1 plus epsilon prime 1 plus epsilon bar prime. Now we're forgetting about the anti-analytic piece. Right, we're just looking at the effect of an analytic coordinate transformation. Okay, so this tells us that, but now we Taylor expand the e to the power 2 phi, that's 1 plus 2 phi. Let's call it delta phi to keep to keep in our minds that it's small. So we get 2 delta phi is equal to epsilon prime. Is this clear? So the Weyl transformation we've done is with 2 delta phi with a Weyl factor such that 2 delta phi is equal to epsilon prime, or delta phi is equal to epsilon prime by 2. All good? Okay. Now, under such a Weyl transformation, we saw that the change in our stress tensor was this object. So let's write this in terms of, we expect the Weyl transformation to just depend on the Weyl factor. Okay? So let's write this in terms of the Weyl factor. Well, it nicely has 3 derivatives. So we can use one of them up to make it this Weyl factor. So let's see, we get delta t is equal to delta phi del z squared by 6 and c. Well, because delta phi already had a factor of 2. So that's what absorbed up the 2 from the 12. Is this clear? Okay. Now, there is a sense in which this Weyl transformation property of T is an anomaly. Okay? And as almost everyone here knows, anomalies, when you have an anomaly in a theory, you often have choices. You can choose to push the anomaly into one symmetry or another. Okay? Now, in a theory where one of your symmetries is somehow sacred, say it's a gauge symmetry, or in our case, coordinate transformation gauge symmetry, we don't want to give that up. Okay? So we make sure that the symmetry that's sacred is preserved, and if there's some other thing that's less important to us, we allow that to be violated. We could choose regulators, we could choose a counter term to switch that around, but that would give us a meaningless theory. Okay? In the current context, we're going to preserve diffeomorphism invariance. Okay? We could actually always violate diffeomorphism invariance, and in doing that, get a stress tensor that has 0 trace. But that's too high a price. Okay? So we're going to preserve diffeomorphism invariance. In particular, we're going to demand that even in a curved background, the stress tensor is conserved. Yeah, these two statements are joined at the hip. Right? A theory is diffeomorphically invariant if the stress tensor is conserved in every metric. These are basically the same statements. Okay? So now let's restore all indices. T was TZZ. So we had delta TZZ was equal to C by 6 del Z squared delta phi. Okay? We're going to demand diffeomorphism invariance and conservation of the stress tensor. So the right-hand side then has to be some sort of tensor. Okay? Some sort of tensor around flat space, because we're working infinitesimally around flat space. Okay? Some sort of tensor, so it has to be the only tensor that will have terms like this. Delta T mu nu is equal to, well, one thing we could write is A times del mu del nu delta phi. But we could also write a B times G mu nu times del squared delta phi. Now, this term, if present, would be invisible to our calculation, because G mu nu, as we have seen, has only Z bar components. There's no non-zero component. GZZ is 0. So we would not see it because we've just computed delta TZZ. Analogous calculation would compute delta TZ bar Z bar. However, we may be forced to include it if we impose consistency conditions. Okay? So this term is purely the ZZ bar piece. So this term, when we specialize to mu nu being ZZ, okay, when we specialize to mu nu being ZZ, no matter what this is, this term is 0. So here immediately we can put C by 6. Right? But what about B? Well, the stress tensor was conserved in flat space. We want it to continue to be conserved. So we want this variation to be conserved. So we want that if I take del mu on the left hand side, which is the same as taking del mu on the right hand side, I get something that is just 0. There's no equation of motion at play here, because this is just about what the metric was. That was up to you. So the only way that that answer can work is if it works as an identity. Okay, so this thing has to be identically 0. But you see, I take a del mu here, that makes this del square. And we're all about flat space, so everything's very easy. Don't have to worry about commuting of any. This guy here becomes del nu, and this is also del square. Okay, so if we take this with a minus sign here, if we choose this with a minus sign here, then this will be conserved. Is this clear? No B. B is now has been set. Is this clear? Because now I get del square times del nu delta phi minus del square times del nu delta phi. So it's just 0. So the only reasonable choice, I mean, we are forced, if we're going to preserve all the things that we want to preserve, to declare that it must be that del T mu nu is equal to c by 6 into del mu del nu delta phi minus g mu nu del squared delta phi. Well, this g, I'm sorry, it was just delta. We're working around flat space. Now, had we done it more seriously, it still would not have, because we would have taken covariant derivative, and covariant derivative moves through g. Okay, but we don't need to be so fancy. Okay, excellent. Excellent. Okay, so this is very good, but as Omkar last time pointed out, it tells us that one of the things we were trying to do, namely to define a theory with the traceless stress tensor, is not working. Because you see, suppose we now take delta mu nu, T mu nu, and take delta of that. That is equal to, this becomes del squared delta phi, but this becomes minus 2 del squared delta phi. Right? So we get minus c by 6 into del squared delta phi. Okay? Now, if something is always 0, its variation is always 0. That's a deep theorem of mathematics. Okay? So if that stress tensor was just 0, if the trace of the stress tensor was 0, this could not be true. So something is wrong. While we were very careful to try to make sure the trace of the stress tensor was 0 in flat space, we could not ensure, we could not cook it up if C was non-zero. To make sure that the trace of the stress tensor was non-zero also in an arbitrary curved space. Okay? Now, this looks sort of worrying unless we can, unless this becomes some sort of nice equation. What do I mean by a nice equation? Okay, so we've seen t equals 0 does not work. Let's be specific, T mu mu. Clear? Okay, but whatever its variation was, the obstruction to it being 0 was proportional to the identity operator. So it's nice. So let's see if we can get away by postulating a new equation, that t is equal to something times the identity operator. Now what could that something be? That something is something that is 0 in flat space. It's built out of the metric because of the delta phi. And because of our sacred principle of coordinate invariance, it should be a scalar tensor. Okay. Now T is an object of dimension 2. Why is T of dimension 2? Somebody? Why is T in a quantum field theory in D dimensions always of dimension D? Excellent. All three of you are saying exactly the same right thing. Okay. Because when you integrate over a D minus 1 dimensional space, namely spatial slice, you can produce energy. Or you integrate another component along a slice, you produce momentum. Momentum and energy both carry dimension E. Therefore, E minus the dimension you've used up by this integration should be the dimension of the stress tensor. So that works if the stress tensor has dimension D. Okay. So the stress tensor here is some object here with scaling dimension D, which means that wherever a metric has no scaling, but derivatives do, so whatever appears should be a two derivative object built out of the metric. So we want a two derivative scalar. Okay, two derivative tensorial scalar built out of the metric. Well, there's basically one choice. It's the Ricci scalar. Okay, so let us postulate that T is equal to some alpha times R, where R is the Ricci scalar built out of our space-time metric. Yes?
Is this true only in some low dimensions, or is this true for arbitrarily high?
Okay, in every even dimension, in any unitary conformal field theory, the trace of the stress tensor does not vanish. Okay, in 4 dimensions, it is there are two candidate terms. Because in 4 dimensions, you would need something that was dimension 4. So you could make something by making quadratic expressions out of the Riemann tensor. Okay, and there are two candidate terms which can come with arbitrary coefficients. In 6 dimensions, there are 3 candidate terms, and so on. Okay, in odd dimensions, on the other hand, there is nothing that can come on the right hand side for the simple reason that it's impossible to make a scalar operator with odd dimensions. Nothing made out of Riemann is scalar with odd dimensions. Okay, so in that sense, odd dimensional conformal field theories are genuinely Weyl invariant. Even dimensional conformal field theories have Weyl anomalies. This thing that we are looking at is called the Weyl anomaly. But one should be scared of the Weyl anomaly, because as we're going to see, it's completely determined by very simple things, especially in 2 dimensions. In higher dimensions, the Weyl anomaly, in supersymmetric theories, it is in the same multiplet, n equals 1 or higher supersymmetric in 4 dimensions. The Weyl anomaly is in the same multiplet as a gauge anomaly, which can then be computed, sorry, not gauge, the UN anomaly, the R symmetry anomaly, okay, which can then be computed by Adler-Bardeen whoever theorem as ABJ, right? By that famous theorem through a one-loop diagram. What? Yes, the usual anomaly, the triangle anomaly, right? So what I mean is that these anomalies are computable, or often computable. Okay, because they're computable, even though the theory is not Weyl invariant, its lack of Weyl invariance is computable. It does not involve additional operators, just involves identity operators. So it's a very tame thing. So odd dimensional conformal field theories are genuinely Weyl invariant. Even dimensional conformal field theory is not so. When they're unitary, never so. Okay? But that lack of Weyl invariance can often be tamed, as we will soon see. Is it clear? Okay. Excellent. So we're going to postulate that T is equal to alpha times R. Now, suppose I have a metric which is delta mu nu times e to the power 2 phi. what is R built out of this metric? When we build R out of this metric, what do we get? Well, I'm just going to write it down for you. Okay, you can do the calculation. Okay, or you can look it up. Okay. Wikipedia, okay. ChatGPT. Okay, okay. So I hope I do it right. The sign I will not swear by, but I think it's right. E to the power minus 2 phi times del square phi. No, 2 phi. Yeah, that's the 2. Yeah, the 2 is correct. Okay, let's look at some features of this formula. This formula, by the way, is exact. Okay, but if we were working to linear order in phi, okay, if we were working to linear order in phi, well, let's first look at the e to the power minus 2 phi. That had to be right, because you see, Ricci scalar is Ricci tensor, R mu nu, and then with G mu nu on top. R mu nu is built out of derivatives of Christoffel symbols. Okay, Christoffel symbols themselves are built out of G inverse G. So I have no net scaling under constant rescalings of the metric. So like Christoffel symbols, R mu nu has no net scaling under constant rescaling of metric. Okay? So R mu nu transforms not at all under constant rescaling of metric. Therefore, G mu nu times R mu nu, G mu nu upper, must transform like G mu nu upper does. But if G mu nu goes to e to the power 2 phi G mu nu, then G mu nu upper goes to e to the power minus 2 phi times G mu nu. Okay, so this term had to be there. At least at first order. The only other term that could have been there, first order in delta phi, is del square of delta phi. It has to be 2 derivative because Ricci is 2 derivative. Okay, has to be linear in delta phi, so what else could you have had? It has to be scalar, del square delta phi. At higher order, there could have been a del phi term. In 2 dimensions, turns out not to be the case. Now that requires more detailed calculation. Okay, and then there is a 2 and a minus, and that I pulled it out of of Wikipedia just before coming. I hope I got the sign right. Okay, okay, fine. This is for, so what is this statement? What is this equation here? For metric, this R is equal to that. Okay, great. Okay, so great. So now, suppose it was true that T was equal to alpha times R. Then under a Weyl transformation, T would be alpha times R of that Weyl transformed thing. Okay, but R of the Weyl transformed thing we've just written down here. To linear order would be minus 2 del squared phi, delta phi. Is this clear? Okay, so what if it was true that T was equal to alpha this, then T should have been equal to minus 2 alpha times this business. Okay, but we know what T is equal to because we've computed how it changed from 0 to whatever. It changed to minus C by 6 del squared of delta phi. Okay, so it all works if we identify alpha as equal to C by 12 R, C by 12. Okay, I won't swear I've got the sign right, but up to the sign, the number is correct. C by 12, I remember. Okay, I'll ask you to check my R formula and so on, for the sign. Okay, and therefore we conclude that it must be that T is equal to C by 12 times R. Okay? Is this clear? Okay? There are many places I might have got the sign wrong, right? At the beginning. Anyway, plus minus C by 12 times R. Okay? Fantastic. Once we've got this lovely formula, we see that even though T is not 0, okay, even though T is not exactly 0, it is something known. Let's put this formula to use. Let's put this formula to use in the following way. You see, we started our lectures by saying that one clear thing, one clear characterization of a while invariant theory is that partition functions of the theory on a metric and a while transform metric are the same. Now a theory is not quite while invariant. So partition function of the theory on metric and while transform metric will not be quite the same. But we should be able to use this formula to find the relationship. Let's try that. Okay. Okay. See, suppose I have Z of delta mu nu. I have the partition function of the theory. I'm saying delta mu nu, but it doesn't matter. Let's call it G naught. Let me at the moment focus on delta. Delta mu nu, but actually will not matter for most things. But times e to the power 2, fine. Suppose I have this partition function, and I want to change phi infinitesimally. I want to change phi to phi goes to phi plus delta phi. Okay? Now, what that does is change the metric. So delta G mu nu is equal to 2 delta phi times delta mu nu. Now, the whole point in life of a stress tensor is that it is the response to a partition function, also a correlation function, if you're doing it away from other operators. But it is the response of a partition function to change in the metric. Okay? And the formula goes along the lines, again, constants, I will ask you to forgive me, but something like 1 by 2 pi square root g T mu nu delta G mu nu is the change in the partition function. Delta Z is equal to this times Z. Times, yeah, this will be an expectation value. And if we had a correlation function, if we were looking at a correlation function, this would be inserted along with all the other insertions. Okay, so this is like expectation value of 1. So this Z is like expectation value of 1. Okay, so it would be that distance. I'm writing this times Z because we usually talk about operator expectation values normalized by Z. So we normally call expectation value of 1 Z, but when we have non-trivial operator expectations, we compute that thing and then divide by expectation value of 1. We are interested in variation of log Z. Fine, exactly. So let's put this Z down here, if you like, and that becomes variation of log Z. Exactly. Now, the great thing about this is that we know everything about this. Because this delta G mu, so we have 1 by 2 pi integral square root G Now delta G mu nu, remember, was 2 delta phi times T mu nu delta mu nu. So that's T. Okay? Is this clear? Times 2 delta phi. So that's 1 by pi times, now we had that C by 12 times whatever we got here, okay, times delta mu nu delta phi times T, which was C by 12 times R, and R we claimed had a minus. Okay, this becomes 6 del square phi. Okay. Excellent. So here, I cancel the square root g, which has an e to the power 2 phi, with the e to the power minus 2 phi in that. And this del square, when I'm writing it here, is just del mu, del A, del A. It's just the Minkowski del A phi. Okay, so this is, let me write it as del square. It's not got the metric in it. Just A. Okay, that was the same, by the way, there. This. I should have said that more clearly. When I wrote what R was, this formula is correct, where del square is not like a fancy del. It's just del mu, del mu. Del square in metric delta mu. Okay? Excellent. So, okay. Now this is our formula for how, and this times z is the change in z. Now can you think of an expression that can we integrate this? It's actually very easy. Suppose we write e to the power c by 3. I'm writing a minus to obey all my signs. I'm not guaranteeing any of those are right. But c by 3, there's a pi integral del phi del phi. Z is equal to this. This del is contracted with metric delta. Del A phi del A phi. Okay? Now let's take the variation. Delta z would be equal to z times the variation of this object. This object would vary because this varies or this varies, so there will be a factor of 2. Then we integrate by parts. Becomes delta phi times del square phi. And we get exactly that. Z times integral delta phi times del squared phi. And I've chosen the number so that the numbers will match. Is this clear? Was that too fast? Okay. So if you have an expression like, so this kind of expression, z is equal to this, gives you, is the integration of that relation. Is this clear? Now, so, if we started with some base metric and tried to go to some other metric. Now, let me first check with Polchinski if he agrees with our factors. What? C by 12. I probably messed up badly. Just a minute. Where has this 3 gone? Just a minute. He gets a by 8 pi and a was a1 was c by 2 or something like that, right? No, wait, c by 6. Sorry, just a minute. A was 12. A was minus 12. Let's see. So he gets, I'll write down what I see in my book. He writes this by A1 by 8 pi. And another equation I see is C is equal to minus 12A1. Okay. So A1 is equal to minus C by 12. By 8 pi. Sorry. I had C by 12. What happened to my 12? Okay, this C by, I did it the other way, right? There was a 2 pi and I had a 12. So it was 24 pi. So I cancelled the wrong 2. So 24 pi, that would become for me 12 pi. Okay, that agrees with what Nikhil wanted, but doesn't seem to agree with what Polchinski wants. C by 12. Just one minute. Sorry, he writes it with, a by 2 pi. A by 2 pi. So now we're off by a factor of 2. He gets minus C by 24 pi. By the way, he agrees with C is equal to, T is equal to C by 12R. So, where did I lose the factor of 2? Just 1 minute. I'll see if I can track it down a bit. There's a 2. Thank you. So that's worse. C by. I messed up again on factor. Okay, let me see if I can correct that. Okay, so you say that I want where I've written 24 it should be 12. Let me just check that I agree with that. Yeah, so 2 from 2 pi and then there was a 12. Fine. So there was a 12. Okay, maybe I can request somebody to track down all factors of 2 and if nobody manages, next class I will give you the correct factors of 2. Okay, sorry about this. Okay, up to factors of 2 we've got it correct. All factors of 3 are correct. Okay. pi. Okay, excellent. Okay, yeah. Now, I'm just going to tell you something, which is sort of interesting. You see, this expression here, which was sort of phi del square phi, okay, can be thought of in the following language. Can be thought of as del square phi 1 by del square times del square phi. Okay? Now the reason I want to do this perverse thing is that while phi is not something particularly nice, del square phi is the Ricci scalar up to various factors that will cancel out with you. See? So what this expression here is something that can be written not just for the particular kinds of metrics that we started out with, that is delta mu nu times e to the power 2 phi, but for any metric, okay, that is coordinate equivalent to this. So what is the counting here? The counting here goes like as follows. By a Weyl transformation and a coordinate transformation, you can reach generically any metric in a two-dimensional space, because the number of components in the metric is 3. There's GZZ, Z bar, and there's GZZ bar. And the number of fields you have in your hand is 3. Now the statement becomes tricky if you look at it in great detail. So for instance, if you're on a sphere, if you're working on the manifold, the sphere, the statement is 100% true. Every metric on the sphere that you can put on the sphere can be brought to delta, or to the round metric on the sphere, by a Weyl and a coordinate transformation. Okay? On the other hand, on a torus, this is not quite true. Okay? In fact, the moduli of the torus are the obstruction to this. The complex structure moduli of the torus are the obstruction to this. Okay? And this is why in string theory, when we do string perturbation theory, on higher genus manifolds, we have to integrate over the moduli of the various manifolds. These are all the metrics that cannot be brought to one another via Weyl transformations and diffeomorphisms. Okay, up to that minor fact, say we're on the sphere, where this is just 100% true. Okay, every metric can be brought to delta by Weyl transformation and a coordinate transformation. We've already understood how things transform on a Weyl transformations. That was not clear from general principles, but we figured it out. Coordinate transformations, well, that's an invariance. So we should have the answer to the partition function for this on the sphere, let's say, for every choice of the metric. And by using this idea, one can work it out a little more seriously and show that the expression that works is something like sigma prime 1 by del square. So 1 by del square is Green's function. Green's function in g of sigma prime r of sigma. And then this integral will involve square root g sigma and square root g sigma prime. Okay, this will be sigma prime. So this expression reduces to this expression for the particular case that the metric was delta mu nu times e to the power 2 phi and is coordinate invariant. And therefore, and since every metric on the sphere can be brought to any other metric by a Weyl and coordinate transformation, it must be the unique correct answer. Okay? So what we have done here is to show that the partition function, even though it's not invariant under Weyl transformations, had been invariant under Weyl transformations, it would have been independent of the metric on the sphere. Because every metric on the sphere can be brought by Weyl transformations, which would then by hypothesis have been an invariance, plus diffeomorphisms, which of course don't change the partition function, it's just a coordinate transformation. Okay? Every metric could have been brought to a standard metric, and so the answer would have been independent of the metric on the sphere. Here, it's not quite independent. But it depends in a completely determined way that depends on the details of the dynamics of the field theory through one number, namely the central charge. Okay? So we've got this very universal behavior for the non-Weyl invariance of this theory. Okay? And this is very powerful, as you see. It tells you that if you know the partition function of the theory on, on the round sphere, you know it for every possible metric you can put on the sphere. Okay? Does not completely determine the partition function on all possible tori because of this moduli issue. This is something we will come back to. We will study conformal field theories on tori and look at modular invariance and all that fun stuff. We will address in this course. Okay? Any questions or comments? Yes?
Here multiplying like
You want to see how the e to the power 2 phi's work out here?
So the thing that I am confused about is the Green's function. How does e to the power 2 phi thing?
How do the e to the power 2 phi's appear in the Green's function? Okay, let's see. Let's try to get everything straight. Okay, so we just want to keep track of overall powers of e to the power 2 phi. Sorry, just one second. Hi, Sachin. Yeah. I'm teaching now. Can you give them the phone? I'll just tell them to let you in. Okay, great. Thanks. See you soon. Bye. Okay, excellent. Sorry, yeah, we were talking about e to the power 2 phi's. Okay, so let's see. So let's get this straight. So how would G be defined? G would be defined as G sigma prime del squared is equal to delta. Now, how is delta defined? Delta is defined with this factor of square root G. Okay, so this will be delta sigma prime. Delta will be defined by integral delta sigma prime f of sigma square root G of sigma is equal to f of sigma prime. Okay, now fine. So now we should now from that be able to figure out okay, so let's say that this guy here this guy here, let's see, well, I'll just see if Polchinski has the answer to your question, otherwise we'll figure it out. And sorry, in fact he defines square root. This is his definition. Square root G okay, see, what we need is the following, right? We need that okay, so square root G transforms like e to the power 2 phi, right? Because G transforms like e to the power 2 phi, and there are two components in G. R transforms like G upper, so e to the power minus 2 phi. Now, what about G? Our answer had just omegas. So, what is the transformation property of G? Well, let's see. Inverse and if G was just not transforming, that would be okay, right? Because this 2 phi and the minus 2 phi would cancel each other from there. Now, let's look at this equation here. I suppose this thing is basically this 1 over. This is probably like the 1 over, meaning this is a delta function without a G. Right, good. So that works then, right? Because there's a G inverse here and a 1 over square root G. So at least the counting works. Okay, we'd have to do it a little more seriously. Okay.
People do this sort of thing in QFTs with a curve background, that you have this type of Green's function and then two path integrals. So that is
Yeah, the Green's function, right, in a curved background, a Green's function is well defined. It's just solution of del square phi is equal to whatever. Yeah, people do this. Okay, excellent. Any other questions or comments? Okay, excellent. So now we have completed all the first round discussion I wanted to have about the general structural properties of conformal field theories. Okay, so in my mind our course was divided into, the 2D part of this course was divided into maybe 4 modules. The first part was just general discussion. That is now complete. The second part is to study free theories in detail. Okay, to study free bosons sometimes with compactification, study free fermions, study bosonization, connection between free bosons and free fermions. Okay, the third part is to study minimal models, and the fourth part is to study Weissenberg-Witten theories. Okay, so we are entering part 2 now. Okay, any questions about the general structure? This is a great time to ask because we're going to switch gears a little bit. Okay, perfect. So let us now try to see whether the structures we have described and try to build up appear in simple examples. And the first example we're going to study is the theory of a free scalar in 1 plus 1 dimensions. Okay, so we're going to study the theory of a free scalar in 1 plus 1 dimensions, and the action for this theory, we will choose the following. S is equal to 1 by 2 pi alpha prime integral of 1 by 4 pi alpha prime 4 pi alpha prime integral square root g mu nu del mu x del mu x. Okay. So 2 comments. Firstly, I've called the scalar field here x. If you don't like that, you can call it phi or h or something like that. The reason I've called it x is that for 1/2 of this audience, maybe 2/3 of the audience, maybe 4/5 of the audience, maybe all of it. Okay. The place where we use this theory most frequently is on the well sheet of the string. In that context, the scalar field x is the position of the string in spacetime. That's why I've called it x. I've also kept the alpha prime for that reason. Okay, We will often work with alpha prime equals half. Okay, we will often work with alpha prime equals half, sometimes alpha prime equals 2, depending on users. Right now we're going to keep this general. Okay, so of course this value of alpha prime is meaningless because it can be reabsorbed into a redefinition of the field, a scaling of the field. So you can set it to any value you want. We will have more meaning once we make these coordinates periodic and so on. Okay, just so that we can always go back, compare back with space-time notions and string theory. For those of you who are interested in doing that, I will keep alpha prime around whenever I'm talking about scalars, much of the time. Okay, excellent. So what is this theory? So let's see. Let us first take this theory and study it in Lorentzian space. Study in Lorentzian space on a cylinder, by which I mean I've got the theory on a spatial S1 and time is time. Okay, so on a spatial S1 I've got the theory and the theory is there in time. Okay, so let's imagine that our coordinates are given by sigma and tau. Okay, sigma lies in 0 to 2 pi and tau goes from minus infinity to infinity. Okay, the metric on which we're working, the metric is g mu nu is equal to minus d tau squared plus d sigma squared. Just a flat circle of size 2 pi, and we have it in time. Okay, excellent. So let's try to take this action and write it a little more explicitly. Okay, so the action is equal to, well, I suppose if I'd really written it this way, I should put a minus sign here. And the action is integral x dot squared minus x prime squared 1 by 4 pi alpha prime d sigma d tau. Okay. Okay, so the first thing we want to do is to quantize this action. Okay, this is of course a very, very trivial thing to do. Okay, so it's of course a very trivial thing to do, and just for fun, let's do it as in a way that will be both fast as well as maybe a little less than completely standard. Let's quantize this theory by first solving it classically, okay, and then finding the symplectic form on classical phase space and quantizing that symplectic form, just for fun. Okay, so let's solve this theory first. What are the solutions of this theory? Well, clearly we can set x is equal to x naught plus sum over n e to the power I n sigma, and let's call this x n that comes behind it. Okay, in space, on a spatial slice, clearly we can expand it this way. We want to maintain the periodicity of this thing. If we want the field to be real, as we will want for, we will have xn is equal to x minus n star. Okay. So we have reality. Okay. Now each of these x naughts and xn's are functions of time. Okay, so what is the equation of motion that each of these xn's and x naughts obeys? Well, if we plug x naught in, it gets no contribution from here. Okay, so we can write this action if we want, just in terms of these various x naughts and xn's. by themselves. We can write this action as just x naught dot squared, and then I get a 1 over 2 alpha prime because the 2 pi integral has been done. Okay, and then plus xn x minus n dot minus n squared xn x minus n. Just by plugging in and demanding that the Fourier modes bang into cancel each other so that the integral is non-zero of space. Clear? Okay, and so we get the solutions x naught double dot, the equations of motion are x naught double dot is equal to 0. So x naught therefore is equal to, as a function of time, is let's say some now c naught plus v naught t, position plus velocity times time, and x n. Okay, now xn obeys the same equation as that of a harmonic oscillator with frequency n. Okay, and so xn is a harmonic oscillator with frequency n, and so its solutions are, let's say, alpha n e to the power I n t plus beta n e to the power minus I n t. Right? So with each of e to the power I n sigma, we could attach either an e to the power I n t or we could attach an e to the power minus I n t. Okay, these are the various time dependencies allowed. Okay, so you see that the most general solution to our equation of motion is x is equal to, what do we call it, c plus v times t plus sum over n zeta n e to the power I n tau minus sigma plus sum over n e to the power minus I now just a minute, tau minus sigma, whatever, I n tau plus sigma. Is this clear? What? Sum over, there's a coefficient, eta n. Okay, so the most general classical solution to this problem, okay, is sum over zeta n's times this plus sum over whatever tau n's times that. Now we will give these guys a name. We will call all such modes, these modes we'll call zero modes, because they originated in the modes that had no momentum dependence. Okay, we will call all such solutions, we will call them right moving solutions. I'm calling them right moving because if you think of sigma, as being like this, we have some sort of wave here. The peak of the wave is determined only by tau minus sigma. And so sigma moves to the right, as the time increases, sigma moves to the right. Okay, and I call all such solutions left moving solutions for the obvious opposite reason. Okay, So classically, we've completely solved the theory. Okay, we've got the solution is a general sum of 0 modes, left movers, and right movers. Okay. Now, in the quantum theory, each of these coefficients will be promoted to operators. Okay, and these operators will obey some sort of commutation relation with respect to each other. Okay, they'll more or less be the commutation relations of harmonic oscillators. Okay, but we want to get those commutations relations straight. So let's start. Okay, so now if we want to know what the right commutation relations of these are, we want basically the classical Poisson brackets on the space generated by these various numbers. Okay, now how is that computed? Well, let's see. The canonical momentum, so what was action? Action was 1 by 4 pi alpha prime integral x dot squared minus x prime squared. Okay, so the canonical momentum for this x field was just x dot 1 by 2 pi alpha prime by 2. Okay, now the fact that x and x prime are canonically conjugate to each other can be written in a slightly more slightly more covariant way in phase space as follows. Imagine we have phase space, which is the space of all solutions. Okay, and imagine that we take a point in this phase space and we do a little variation of that point. Okay, the variation of that point around the point we're starting with is the tangent space of that point in phase space. We've got a very simple phase space, it's flat here, so none of the power of what we're saying is required, but just it's fun, so we can do it. Okay, now on that phase space we define a symplectic form, and that symplectic form is basically the thing that is going to tell us our PQ commutation relations. Okay, so the way that's sort of nice is to define a symplectic current. Okay, and then integrate the symplectic current over space to get your symplectic form. Okay, and the symplectic current for this theory is comes from the observation that this. So for the symplectic current we want basically del p wedge del, the thing that when integrated will give you del p wedge del q, and is basically the following thing. It is del mu delta phi wedge delta phi and then 1 by 2 pi alpha prime. Okay, this is the current without the integral. The 1 by 2 pi alpha prime is the same as this. This del mu of delta phi was this x dot here. If we were evaluating in time, it would be this x dot, and this is x. This is basically capturing that x and x dot are canonically conjugate to each other with this functional delta function integrated over. Okay, so if we take the symplectic current and we integrate it over sigma, let's take the current with 0 component and integrate over sigma, we will get the symplectic form. Okay, so the symplectic form is x dot wedge delta x wedge and x dot wedge delta x divided by 2 pi alpha prime integrated d sigma. Okay? And this, we can now put our classical solution into this expression and thereby find the symplectic form for all the coefficients that appear in the coefficients parametrizing our classical solution. Okay? Let's do that. So what we're supposed to do is to take integral d sigma, put delta of x dot, wedge delta of x 1 by 2 pi alpha prime, where x for x dot we just take for x dot we just take the derivative of this expression here, the time derivative of this expression here. So x dot is what? So this is 1 by 2 pi alpha prime integral d sigma, and then we get delta v. Okay. Then from here we will get in plus in sum over n in times delta zeta n times e to the power in tau minus sigma. Okay, and here we will get also in the nu n times e to the power in times tau plus sigma. That's the first term. When we take wedge of just delta x or whatever that is, so we take delta c wedge, and let's say that we're doing this at t equals 0. Okay. So we take deltas, tau equals 0. So here everywhere imagine in your head that it's 0. Delta c plus sum over n delta zeta n e to the power I n tau minus sigma, always tau 0. It of course won't matter. Plus sum over n delta nu n e to the power I n tau plus sigma. Okay, this is the expression we want. Now, now we have to evaluate the integral over sigma. Let's first look at the zero modes. Okay, the zero modes will give us delta v wedge delta c. Okay, why was this 1 over 2? There was 1 over 2 pi because that's fine. Okay, so this will give us delta v wedge delta c. So this part gives us delta v wedge delta c. Okay. Then there are these guys times these guys. Okay. Now, here we're going to get the following. There are the expressions that come left movers with left movers, right movers with right movers, right movers with right movers, left movers with left movers, and potential cross terms. Okay? The cross terms are going to cancel each other, as we will see. Okay? So let's work out first the left movers with the right movers with right movers. Okay. So the right movers with right movers are what? We get in delta zeta n. Now this guy only clicks when it hits delta zeta minus n. Wedge delta zeta minus n. Okay? And this thing is summed. is summed over all n, positive and negative, but not including 0. Okay? Then we also have this guy with this guy. Where is the t dependence? You see, that also vanishes because the exponentials, because everything was a function of sigma minus tau. So the integral vanished only when the sigma dependence cancelled. Therefore, the tau dependence also cancelled. Okay. Okay. Plus the thing that we'll get from the right movers is basically the same. Sum in delta nu n wedge delta nu n. Okay. And then there are the left movers with right movers and right movers with left movers. Okay. Here, when we work it out, we're going to get, it's going to cancel because of the antisymmetry of this wedge. Because we're going to get a delta zeta n wedge delta nu n from here with an in, but also from here, and then there's the antisymmetry. So I'll leave you to check that just cancels. Okay? So the symplectic form is non-zero only between right movers in themselves, left movers in themselves, and the zero form. And the zero modes. Now the symplectic form that we wrote here was delta p wedge delta x. Okay, it was delta p wedge delta x. Okay, so the form that we are going to get will also be like a delta p, p with x. Okay, so now we can immediately translate this to commutation relations. Okay, because the first thing to remember is that the symplectic form and omega that appears inside Poisson brackets are inversely related. Okay, so a symplectic form is omega mu nu, d zeta mu, d zeta nu, wedge d zeta nu. But it's Poisson brackets require taking derivatives and require inverse of omega. So once you have the symplectic form, you're supposed to take the inverse of that, and that gives you Poisson brackets. Okay, so the Poisson brackets that we have are basically that C and V is equal to 1. Okay, and now we have to keep our wits about us because of this inverse business. This guy will get delta zeta minus n, Poisson brackets delta zeta n is equal to 1 by in. Because we had to invert. Okay, and similarly, delta nu minus n delta nu n is equal to 1 by in. Okay, now when we move to commutation relations, you see, once we have a Poisson bracket, we add an I on the right hand side to get commutation relations. Okay, and so we have C commutator V is equal to I. This is just position momentum commutation relation because the zero mode behaves like position and momentum for a particle. That's the standard thing. And we will have, there's no delta. Yeah, okay. In this Poisson brackets, there's no delta. It's just this. And then we have commutation relation of zeta minus n, zeta n is equal to 1 by n. And nu minus n, nu n is equal to 1 by n. Okay. Okay. Let us stop the class here. And in the next, so basically these are harmonic oscillators, right? What we've got is a bunch of harmonic oscillators here. In the next class, we will take this forward, complete the quantization, which of course is a trivial exercise, and then study this theory as a conformal field theory. Okay. No, because this is omega with mu nu. And we have to first invert it. So n becomes 1 by n. Yeah, so this omega, think of this as 2 cross 2 matrix. Clear? Well, the answer is n depending on your normalization. We normally, we'll see, but we expand x as sum over alpha n divided by n. Okay, that absorbs 2 powers of n, therefore we get n. Right now I have not done that fancy thing. We will. With whatever normalization we work, we'll get a commutation relation. Here we just started with the most straightforward thing, then we'll go to what is convenient.